In this class, we will learn about ways to measure zero electrical resistance in superconductors. Persistent current influence of magnetic field, critical current density and isotope effect on superconductors. How to measure electrical resistance in superconductors. We know that superconductors have zero electrical resistance. It is fundamentally not possible to test experimentally whether the resistance is zero. There are two ways to determine transition to superconducting state. First method is to measure the potential, that is voltage, across the material. A potential difference, V, is applied across the material. When the temperature is greater than critical temperature, from figure A, you can see a voltage drop is observed across its ends because of resistance. When the temperature is less than or equal to critical temperature, that is, a material behaves like a superconductor, from figure B, you can see there will be a very large current. From the equation V equal to IR, the resistance will be equal to zero. Simply the potential difference disappears. Second method is to measure current. This is more sensitive method when compared to first one, measuring voltage. This method was devised by Kamerlingh Onus. It consists of measuring the decrease of a current in a closed ring of superconducting wire. Take a closed superconducting ring. Apply a magnetic field when temperature is greater than critical temperature, that is, the material is non-superconducting material. Now cool it to below the critical temperature, so that it becomes superconducting. When an external magnetic field is switched off, a current is induced in the ring. This is because of Faraday's law of induction. A change in flux induces current. If the ring had a finite resistance R, the current circulating in the ring would decrease according to the equation, where L is the inductance of the ring. If the resistance is zero, the current is going to exist for a lifetime. This current we call it as persistent current. Now we will discuss about persistent current. Once a current is induced in a closed loop of superconducting material, refer before figure, it will continue to keep flowing, of its own accord, around a loop as long as the temperature is less than critical temperature. Such a steady current which flows with diminishing strength is called persistent current. The persistent current does not need external power to maintain it because there does not exist power, I²R, losses. It persists for more than 10⁵ years, theoretically. In one experiment, they found current can be maintained in a superconducting loop for more than 2 years. These superconducting coils with persistent currents can produce magnetic fields and can therefore serve as magnets. Such a superconducting magnet does not require a power supply to maintain its magnetic field. In this section we will see effect of external magnetic field. We have seen superconducting state depends on the critical temperature, Tc. A material can change from superconducting to normal state even if the temperature is less than critical temperature, that is T less than Tc, because of external magnetic field or total current density. Kamerlingh-Onnes in 1913 observed that superconductivity vanishes if a sufficiently strong magnetic field is applied below critical temperature. The minimum magnetic field which is necessary to regain the normal resistivity is called critical magnetic field, HC. When the applied field exceeds critical magnetic field, the superconducting state is destroyed and the material goes into the normal state. Value of HC varies with temperature. Dependence of critical field on temperature is given by the equation. From the graph we can observe that as the temperature decreases, the magnetic field needed to destroy the superconducting state increases. In this section, we will discuss about critical current density. The magnetic field which destroys superconductivity, as discussed before, need not to be necessarily the externally applied field. It may be the magnetic field produced as the result of current flow in the superconductor ring itself. We know that current produces magnetic field. If the field produced by itself exceeds critical magnetic field, the superconductivity of the ring is destroyed. The material will change to normal material. The maximum current density J at which the superconductivity disappears is called the critical current density Jc. This effect was observed in 1916 by Silsby and is known as Silsby effect. A superconducting ring of radius r ceases to be a superconductor when the current is given by the equation. Variation of current density and magnetic field with respect to temperature is shown in figure. In this section, we will discuss about isotope effect. What is meant by an isotope? All isotopes of a given element have the same number of protons but different numbers of neutrons in each atom. Critical temperature of an element depends on the atomic number. It was found experimentally that the critical temperature is inversely proportional to square root of atomic number. Graph shows critical temperature with respect to inverse square root of mass for different isotopes of mercury. In next class, we will discuss about Meissner effect London penetration depth. Thank you.